This is Unit 1, the alphabet and grammar of geometry. Preview video 1.2, the logic of geometry. Sit tall wherever you're at. Do this a couple times. Ready? Inhale through your nose. Hold your breath for 3. Exhale 5. Close your eyes. Come on, inhale 3. Hold. Exhale 5. Take a deep breath. Open your eyes. Taking a look here, you're at this preview video 1.2, the logic of geometry. For this particular lesson, you're also going to need your reference booklet handy. So go grab your reference booklet. At some point, you're going to be writing in it. Don't forget date, time, location, as well as a parent or guardian sign-off. Previous lesson, we talked about radicals. You're going to do this video on your own. And then you're going to pause the video, and then you're going to restart it and correct in red pen. Ready? Pause the video. All right, students, welcome back. You're correcting in red pen. If you think you know what you're doing, speed through just to the answer, or you can follow along with the explanation. When we multiply and divide radicals, all you have to remember are these 3 steps. Innies, outies, simplify. Innies, outies, simplify. Innies, outies, simplify. This is what I mean. Innies. You're going to be multiplying the innies. So we have a square root and we have 6 times 12. Why didn't you do 6 times 12? Because the key to multiplying is not to multiply. It's to factor. Outies. 5 times 3. Now you take the 6 and the 12, and we're going to factor both of them. You're looking for dates. The dates come out. I have a pair of 2s. They're going to come out as a single 2. And that's it. I have a pair of 2s. Everything else, oh, nope. Take that back. You have a pair of 3s. We're going to grab them and come out. Pair of 3s. So cancel the 2s, cancel the 3s. And now on the outside, you multiply. 3 times 2 is 6. 6 times 5 is 30. 30 times 3 is 90. Another way to do this would be 6 times 15. Which is still 90. So on the outside, I have 90. So we got rid of a pair of 2s and rid of a pair of 3s. So what was left was this 2 right here. And so it's going to be 90 root 2 would be your correct answer. After you factor, the key to multiplying is to not multiply. It's to factor. Okay, over the next about 20 minutes, you're going to kind of wonder, am I even in a math class? Because gone are numbers. Goodbye, numbers, for the next about 20 minutes. We're going to be talking about the grammar or the logic of geometry. So, keywords: inductive, deductive, converse, inverse, law of contrapositive, and conditional. Geometry is a language. Geometry is a language. The English language. So when you learn English, the English language consists of 26 letters. The geometry alphabet only consists of 5 letters. And those letters are a point, a line, a segment, a ray, a plane. These letters form the whole total of geometric diagrams. All geometric diagrams are only made up of 5 letters. Today, we're going to discuss the grammar, not the letters, but the grammar of geometry, grammar to go with the language, also known as geometry logic. The terms you need to be familiar with are conditional, converse, inverse, contrapositive, inductive reasoning, and deductive reasoning. All of these vocabulary words feed into the type of logic or the grammar of the language of geometry. So you're going to need that reference booklet in about 15 minutes. So a conditional statement, believe it or not, you are surrounded and swimming in conditional statements. A conditional statement is an if-then statement. It implies directly or indirectly a cause and an effect, if then. Now, sometimes if and then aren't directly stated, but indirectly implied. Where do you see this indirectly implied? All commercials. Okay, all commercials. And electronic ads or memes even. Advertisements of certain kinds are conditional statements, even if you don't see the word if then. So here's a logo for Walmart with a very simplistic sales pitch. Walmart, save money, live better. And that's communicating this cause and effect statement. If you shop at Walmart, then you will save money and live better. What's the cause? The cause is you shop Walmart. And the effect, according to this ad of shopping Walmart, is save money, therefore you live better. So cause, effect, that is a conditional statement. Sometimes you will see the phrase if and then, other times it's indirectly implied. In any conditional statement, the cause is also known as the hypothesis, and the effect is called the conclusion. There are 3 additional ways a conditional, remember, a conditional is a cause and effect statement, also classically known as if-then. There's 3 ways it can be modified. Now, when we start with a conditional, the if statement or the hypothesis, we generally use the symbol of P, and the conclusion statement, we use Q. Where did P and Q come from versus any other variable? Someone decided it was easy to write decades and decades ago. So we use P for the hypothesis, Q for the conclusion or the pieces of a conditional statement. The phraseology of then or causality, we use an arrow. So converse, inverse, contrapositive. Converse. You switch. Inverse, negate. Contrapositive. Switch and negate. Now that makes no sense to you at this moment. Totally okay. Just write the symbols down. As soon as I give an example, it'll be like, oh, it's not that hard. So if this is your original conditional, if P then Q, to switch it, you would write it like this. If Q, then B. Whoa, that's what switch means. Negate means to say the opposite of, and the symbol we use for opposite is this symbol. It looks like a Spanish tilde. So we're going to say the inverse is to negate the original. So opposite of P, therefore opposite of Q. Switch and negate is opposite of Q, then opposite of P. Let me keep my color straight here. Opposite of P. All right. A lot of you are starting to scratch your head like, what is going on? Where's the numbers? This is a math class. What's happening? I promise you, you'll understand this. Okay, but you're going to have to get physical and kinesthetic. That means do stuff physically. Ready? Put your hands up like this. All right. Do this with me, folks. Those of you, it's just, trust me, this will help. So we go like this. The conditional is going to read, if, then. Got it? That's a conditional. Conditional. If, then. Converse, switch. Go back, the conditional. If, then, converse, switch. Inverse, flip. Inverse, flip. Back to the conditional. Contrapositive, switch and flip. Ready? Contrapositive, switch and flip. Now you've probably thought your teacher's probably just about lost her mind right now. What are we doing, like these wonky hand signals? It's going to help, I promise. Let me give you an example so you can track with me here that might bring it down to real life. Here is a conditional statement, cause and effect. If it is sunny, then we'll go to the beach. Notice I'm emphasizing if, then. If it is sunny, then we go to the beach. I'm going to use the symbols. If it is sunny premise, I'm going to call that P. Then we go to the beach. I'm going to call that Q. If sunny, then beach. I'm going to shorten it. You can do it with me. If sunny, then beach. Converse, switch. It now reads like this. If we go to the beach, then it is sunny. You see the difference? I'm going to abbreviate it just to make it easier. So the converse is going to read like this. If we go to the beach, then it is sunny. So the symbols would look like this. If Q, then P. That's called converse switch. Inverse, flip. That means you keep the original and you say the opposite. So the original is if it's sunny, then we go to the beach. It reads like this. If it is not sunny, then we won't go to the beach. That's the inverse. You keep the original, say the opposite. If it is not sunny, then we won't go to the beach. I'm going to really botch the grammar just for space sake. Don't tattletale it to your English teachers. No going to the beach. And it reads like this. Opposite of P, arrow, opposite of Q. Negate P, negate Q. That's called the inverse. Contrapositive, you do both. So if it is sunny, then we go to the beach, switch, and flip. And it reads like this. If we do not go to the beach, then it is not sunny. That is the 3 different variations that you need to be familiar with of an original conditional. And there are mathematical things that we're going to do with this, but I'm giving you very simple examples. Ready? I'd like you to take this conditional, walk it through the converse, inverse, contrapositive, and then restart and get ready to grade. Pause. Welcome back. The original conditional says, if you eat an apple, then you've eaten a fruit. Converse switch reads like this. If you eat a fruit, then you've eaten, I'm shortening the grammar again, eaten an apple. That's the converse. Inverse, you say the opposite. If you haven't eaten an apple, if not an apple, again, don't tattletale for the grammar shortening here. Then if you've not eaten an apple, then you have not eaten a fruit. That would be the inverse flip. Contrapositive, you switch and flip. So it'd read something like this. If you've not eaten a fruit, then you've not eaten an apple. That's the switch and flip. Okay, hopefully you got those variations, and if you flipped one of those wrong or switched it wrong, correct in red pen, write a note. Now we're going to analyze what's called a truth value. A truth value. We're going to determine the truth value of each statement. So the first statement, the original conditional says, if you've eaten an apple, so eat an apple, then you've eaten a fruit. And you think, is that a true statement? Well, yeah, an apple is a fruit. So if you've eaten an apple, you have eaten a fruit. So check, true statement. Let's do the converse, the switch. If you eat a fruit, then you eat an apple. So if you tell someone, I've got a piece of fruit packed in my lunch, they pull it out, they start eating, and they have to be eating an apple. Is that a true statement? No, it's not. They can have a banana in their lunchbox, or a peach, or a plum. So the converse of the original conditional is not necessarily true. Now, if they have an apple in their lunchbox, it's true. But in geometry, something is true only if it's always true. If there's a single exception, we have to call it false in mathematics. So something is true only if it's always true, not the exception to a rule. Let's try the inverse. The original was I'm eating an apple, I've eaten a fruit. The inverse says this: if I don't eat an apple, then I don't eat a fruit. That's a false statement, because I could say I'm not going to eat, like a banana. So it doesn't, not all fruits are apples here. So this is a false statement. Things are true only if they're always true. Last one, contrapositive. The original was if I eat an apple, then I eat a fruit. That was a true statement. We're going to switch it and flip it, switch and negate, and say, if I don't eat a fruit, then you don't eat an apple. So if I say I don't eat fruit at all, then have you eaten an apple? The answer is no, because an apple qualifies as a fruit. So this would be a true statement. So here is the connection. If your conditional is a true statement to start with, only the contrapositive is forced to be true. The inverse and the converse are question marks. They're like maybe true, maybe not true, depending on the circumstance. So if a conditional is true, only the contrapositive is forced to be true. However, if a statement's conditional and contrapositive are both true simultaneously, if a conditional and its converse are both true together, we call that statement biconditional. A lot of geometric true statements are biconditional. If an angle is 90, then it's a right angle. Converse. If an angle is a right angle, then it's 90. In that case, they're both true. That would be a biconditional statement. So manipulations of conditional statements, you need to be familiar. There's also two types of primary types of logic: inductive and deductive reasoning. I want you to take a quick look here. These are all different pro golfers in action. Just kind of take a glance. And let's say you had the money to do it, you had the time to do it, hundreds and hundreds and hundreds of pro golf matches. And just kind of take a note here, golf. There seems to be a norm here, probably because you don't want the sun in your eyes when you're trying to hit a little tiny ball. You should notice that in every picture here, and most likely in real life, that there is a hat. Okay? So imagine you know nothing about professional golf attire. So to learn more, you decide to attend all the professional golf matches in a single year, and you observe very carefully every golfer's outfit. After observing hundreds of professional golfers, you conclude that if someone is a professional golfer, then he or she will always wear a hat on the course. Notice the if and then. That's a conditional. Therefore, you come to the general conclusion that all, circle the word general, all professional golfers wear hats on a course. This is an example of inductive reasoning. Inductive. You take in information and come to a general conclusion. Aha! If you're a professional golfer, you always wear a hat on the golf course. That's called inductive reasoning. You take in observation, you come to a general conclusion. I call it the aha statement. Okay, so that's called inductive reasoning. You do observation, and if this was a science experiment, you would do some sort of testing, and you would come to a general truth. And our example, our truth was, if you're a golfer, pro golfer, then you wear a hat on the course. Okay, that's inductive. Deductive says this: you start with a general truth and you apply it to a specific situation. Start with a general truth and you apply it to a specific situation. So the way I symbolize this, you start with an aha, and then you apply it to something specific. So point to something specific. So inductive, take in information, aha, general truth. Deductive, aha, general truth, apply it to a specific situation. Let me go back to our golf example. After multiple observations, you come to the conclusion, the truth, that all professional golfers wear hats on a competitive course. Now, let's say you meet a Mr. Tin Vu at a restaurant, and he tells you he's a professional golfer. He's sitting in a restaurant, fancy restaurant, obviously, in a full suit and tie. He doesn't have a hat on his head at that moment. What assumption can you make about his choice of clothing when he's on the golfing green? And you're like, you got in your head, all golfers wear hats, while on the golfing green, you have a gentleman in front of you, not at the moment wearing a hat, but because he tells you he's a golfer, you apply the truth. Therefore, Mr. Tin Vu, Mr. Vu wears a hat while golfing. This is an example of deductive reasoning. Inductive reasoning discovers truth. Deductive reasoning applies truth to a specific situation. What I'd like you to do, please, is you're going to read these scenarios and you're going to check whether it's inductive or deductive reasoning. Pause the video. Welcome back. You should have a red pen. Write notes. If you got it correct, star smiley. If not correct, make yourself a note here. It says, you know that all Olympic athletes must win at a national level prior to competing in the International Olympic competition. Gabby Douglas competes in the 2016 Olympics. Therefore, you conclude she must have won at a U.S. gymnastics championship. Here, you started with the truth and you applied it to a specific situation, Miss Gabby here. That would be an example of deductive reasoning. You are testing a hypothesis that the rate of falling items does not change depending on its mass. From the same height, you conduct hundreds of experiments by dropping items of different mass at each time. Both items hit the ground at the same time each time. You conclude, light dance, that the atom falls at the same rate, regardless of math. Conclude, you come to a general truth, that is inductive reasoning. The discovery of a truth. The good news for you, my geometry students, is that most of the discovering path of truth in inductive reasoning has already been solidified or done, the heavy lifting, if you will, over thousands of years by great mathematicians from around the world, including some of these names you know, some of them you should know: Pythagoras, Plato, Euclid, Hypatia, Brahmanputra, Khayyam. All of these are mathematicians from all over the world who had an experimental process that related to geometry specifically, and they discovered the variety of truths that we use in geometry. Now, where do you find all these truths in geometry? The truths of geometry we call definitions, properties. Postulates and theorems. Where do we find these truths? You find them in your geometry reference booklet. Ready? I'm going to show you where they're at, and then we're going to summarize some algebraic truths that we're going to use in class. So right now, find your reference booklet. Go ahead, go to your reference booklet, and let me show you where those truths are. You flip here. It is called the DPTP. Definitions, properties, theorems, postulates. Definitions, properties, theorems, postulates. All the truths, quote unquote, that you are going to use in geometry, every single one of them the entire year, are somewhere on these pages. Okay? So just kind of be familiar with it, kind of flip through it. But for now, I'd like you to find Unit 1 and flip in a couple pages until you come to algebraic properties. We're going to very, very quickly recap the different algebra properties that you used last year, your truths that we're going to do examples of in class time. So I'm going to get large print, have this handy. I'm going to go kind of fast because you've seen this before. Ready? Called the distributive property. Notice I add or subtract on one side of an equal sign. You guys know it as collect like terms. I'm going to require that you know this term. This is called addition and subtraction of real numbers. Adding or subtracting on one side. Notice the equal sign here. Since I'm on the same side of the equal sign, I can divide stuff out and reduce to my heart's content. So here we go. 2 goes into 16 8 times. 15 divided by 5 is 3. 20 divided by 5 is 4. And then I multiply straight across. I have 3 over 32. Basically, all my multiplication and division was on one side of an equal sign. I'm not clearing stuff. That's called multiplication and division of real numbers. Not to be confused with the next two. Watch carefully. I'm solving for x. I'm going to add 2, add 2. Notice I'm adding, or you could be subtracting across an equal sign. That is called addition subtraction property. Cross an equal sign. Here, I'm going to solve for x, 1/4. I'm going to times by 4 over 1, both sides. Multiplying across the equal sign, both sides, that's the multiplication property. Dividing both sides, that's called the division property. You're still in your reference booklet. When I have two ratios forming a proportion, I can do this. That's called the cross multiplication property. This cross multiplication property. Couple rules here. Always draw your cross multiplication arrows. Also, do not distribute and cross multiply at the same step. Those are separate steps. Notice I didn't instantly distribute. Careful, kiddos. Watch carefully. I do this. Do not follow me. What I'm about to do is incorrect. Oh, I have a 2 here. So I'm going to divide out the 2 and I get x equals 32. This would be incorrect. The opposite of squaring is not dividing. The inverse operation of squaring is square rooting. That 2 and that 2 do not cancel each other. This is an exponent. So right here, put under the don't do this sign, you don't divide that 2 out. The opposite of squaring is square rooting. And the opposite of square rooting is squaring. So in this case, if I wanted to solve for x, I'd end up with x equals 8. And square root of x squared would give me x equals 36. Left-hand side, this was a don't do this. These are both correct. Square root property. We're almost done. Substitution, if I have 3x equals something and I define my value of x, I'm going to circle it, draw an arrow, plug it in. Notice what I did, circle, arrow, plug, get used to that. Substitution property says, therefore, my answer is 24. These is a real critical differentiation. X plus x, you have 2 x's. X times x, x squared. Do not mix those up, my friends. Those are algebraic truths that you learned last year. Summarize today's lesson and write out your work. Thank you.